So this workshop, as I mentioned, is funded by the NSF HDR project with the same title as the workshop. It's a collaborative project between University of Minnesota, Colorado State University, University of Wisconsin, Penn State, and University of Virginia. And its goal is to develop a framework, a knowledge-guided machine learning framework that uses the unique capability of data science models to automatically learn patterns and models from data, but without ignoring the treasures of accumulated scientific knowledge. And on the right side of this slide, you're seeing the KGML team, the 10 investigators that are leading this project collectively, and they're also leading the sessions that you will be participating over in the next 3 days, and you will get to see them one-on-one. So let me start with the introduction to the KGML paradigm and why we're holding this workshop and where we're planning to go from there. So we're in the middle of a big data revolution, and it's enabled by the confluence of three factors: the advances in machine learning, advances in computing, and that are fed by the big data that has been growing at ever greater speed. And the confluence of these three have revolutionized all aspects of our life. Now, this revolution has been sort of going on slowly for the last 4 decades, but it accelerated in the last 2 decades. And it has really picked up huge steam in the last 5 to 10 years because of, again, the rapid advances in all of these three areas. And as a result, it has completely changed the way we live, we interact with each other, we entertain ourselves, we even elect leaders. And certainly it has completely transformed the commercial landscape from many, many perspectives. And I don't have to belabor the successes. You see them in your life daily. And the fact that we're able to hold this event for 1,000 people is sort of a testimony to that, this revolution. Now, given that these techniques have been so successful in the commercial arena, there is an increasing interest in being able to use the power of this data revolution for accelerating scientific discovery. And again, this is sort of what's coming in from this push is coming from the broader scientific community. And you see that in these cover pages from the iconic journals like Nature and Science. And as a result, NSF, National Science Foundation, most recently, created a list of 10 big ideas, NSF's 10 big ideas, and harnessing the data revolution for scientific discovery is one of those major 10 ideas. So that's sort of the topic of this workshop. However, the straightforward applications of machine learning that have done dramatic, that have sort of given dramatic performance in the commercial non-scientific arena have often shown very disappointing results when they're applied to the scientific domain. And there are a number of reasons for that. And of course, this disappointment has led many people in the scientific community to distrust these methods. And there are many reasons for this disappointment. And one of them is that many of these scientific problems are such that they require a huge amount of data. And even though the data is increasing in richness, in size, in variety, in scientific domain as well, but the kind of data that we need for some of these very complex, latest state-of-the-art machine learning algorithms to work is actually much, much larger. And in absence of that, these models can give you results that are not very good, or they may look deceptively good on the small training data set, but generalize to out of sample scenarios. They can also create physically inconsistent results, in the sense that if you're trying to predict the behavior of a large scientific enterprise, there are multiple components of it, and then they all have to sort of, there are some special relationships that they have to observe, like the conservation of mass, energy, and so forth. And machine learning algorithms not being aware of these can sort of course certainly create inconsistencies, which is another reason to believe that they would not generalize to out of sample scenarios. And this problem of generalizing an unseen scenario is actually a real one, because no matter how good a machine learning algorithm is, it's still finding statistical patterns, however complex, in the data that's provided to it. That means it cannot look for completely unseen scenarios. For example, if you're looking at the weather, the climate system behavior in the current climate, the machine learning may not be able to predict what would happen in a completely different climate because of non-stationarities and such. And the very last reason is that even if my black box method really is able to provide valuable, actionable insight, it does not necessarily advance the science, in the sense that science sort of builds on understanding of facts, and then you sort of build models, and you build more and more complex models, and you understand the system at a progressively greater detail. And a poster child of, and there are many such cases, but I'm just picking this up, is about several years ago, Google had this Google flu trend. They sort of basically started predicting the outbreak of flu based upon the queries people do on the internet. And they were able to show that they were able to predict the flu outbreak. They were able to predict the flu outbreak a couple of weeks before the CDC could do it. And of course, that was very interesting, very exciting, and except that they, as the system was put in place and started predicting, and a few years later, the predictions sort of became completely out of whack, in the sense that they were completely out of the reality. And again, the same issue that you're seeing here sort of came up here. So what we're looking at now is this sort of the two different worlds, the community of data scientists, machine learning people who work in computer science, coming from statistics and computer science and related disciplines, who are building these data science models, statistical models, machine learning models. And they are beginning to show tremendous performance when you're talking about massive amount of data, to the point that you can almost say that you don't need theory. And again, this is, of course, an oversimplification, but there are cases, like, for example, translating a language from translating text from one language to the other. One could sort of say that the best performance today is obtained by pure data science models that simply are making use of this trillions and trillions of sentences that are available on the web, rather than the ones that are making use of the linguistic theories. So you have situations where if you give massive amount of data, you could almost ignore the scientific theory. But of course, in most applications, you don't have that situation. You have much less data. Then on the other hand, you have a situation in which you have a complete understanding of your mechanistic understanding of your physical system, and then you can make all kinds of prediction, but that happens very rarely. I mean, of course, a poster child of that would be like using the Newtonian physics, you can predict the motions of the planets, to the extent that you can launch a probe to Mars, and everything is in motion, and yet the probe would land on Mars many months later, exactly at a point that you expect it to. But most situations that we deal with are much more complex. For example, if you're trying to predict the location of a hurricane or a tornado, or the extent of floods, or something even a lot more complex as the sensitivity of the climate to greenhouse gas emissions, the science that is needed to fully predict them is far from complete. And that's where this notion of being able to use the data to help sort of comes in. But then both of these paradigms, if you do them one at a time, they have both limitations. And I must say that they are not exclusive, in the sense that the scientific paradigm, of course, always uses data, and data science model, no matter how simple and black box they are, they have some notion of theory. But the goal here is to see whether we can accelerate the scientific paradigm by using some of the latest state-of-the-art machine learning advances that have really revolutionized our life. So to that extent, sort of there is this movement in the community, a broader community, to look for models that are guided by theory, guided by scientific theory, and then make use of the latest data science advances. So we have sort of named this paradigm as the theory-guided data science models. And it sort of builds on the foundation of the data science, but taking full advantage of the domain theory. And again, this idea of bringing these two things together, of course, has been pursued in many disciplines by many scientists independently. towards, and people have worked on this idea. And again, just to give an example, even in our own group, we have sort of gone back to as early as 2014 to talk about it. But more recently, in a paper in 2017, it sort of tried to formalize this paradigm, tried to talk about how many different ways the data science models can come together to help the scientific discovery. And this paper, even though it was written more than 3.5 years ago, had a coverage of about 50 plus papers from completely different disciplines who, without knowing or knowingly, were pursuing this paradigm in their respective disciplines. Now, given and because of course so many people have been talking about it, so people have referred to this from many, many names. Somebody has called it knowledge guided, science guided, physics guided, physics informed, physics aware. In these works, physics or physics guided oftentimes isn't generally interpreted as science or knowledge or scientific knowledge. So there are all of these terms, you will sort of find them being represented in many of the literature. Now, because of course the utility of this combining theory and data science, you have this knowledge guided machine learning paradigm applicable in every single scientific discipline that you can think of. And the work in this direction has been accelerating, with greater and greater speed. And you can sort of see that in this survey that we put together just a few months ago, integrating physics-based modeling with machine learning, again, physics being sort of more generally interpreted here. And the survey covered about 300 papers, most of which were published in the last 3 years. So this sort of tells you the amount of excitement people have in this area. And this is also reflected in the announcement from the funding agencies like the Department of Energy, DARPA, and such. There was a 20-year roadmap for AI that was produced by the NSF and Computing Community Consortium, and it highlighted this topic, in certain ways. And there are many meetings just that are purely focused on this topic of bringing physics or the science and data together. Just in 2020, in addition to the meeting that you are attending, which happens to be the largest one, there are like 5 other meetings in the rest of the year that you can sort of see here being planned or have happened. So this again shows the excitement that's generally available in this area. So the goal of this workshop is to sort of bring this excitement to the community, to assess the progress we have made so far, and by bringing the community, wider community, which is of course very large, so we have only a small subset of it, and to also discuss some of the progresses people have made and the challenges that face us in making the field forward. So what I'm going to do is, in my opening talk here, is list some of the questions, and this is not an exhaustive list, but these are some of the questions that are being addressed by many of the talks in this workshop. So one of them, for example, one could ask is, well, physics models are used for all sorts of things in every scientific discipline, or the mechanistic models are used for all sorts of problems. To what extent we can even consider replacing them with machine learning models, even in limited scenarios, in the sense that even if you're not worried about generalizability and physical consistency, but just being able to predict with better accuracy or equal accuracy what the physics models can do. And this is a non-trivial question because the models come in such greater variety. Some of them are much more complex than the others. So the answer of this question doesn't have to be yes all the time. But more importantly, what we sort of aim to see here is what additional advances have to be made in machine learning framework to really make them more suitable for modeling the physics, even if we were just looking at the predictive accuracy. So this is a broad question. And again, you will see that being addressed in many, many talks here. Then the other question would be, now if I'm trying to put knowledge into machine learning models, can I, this is the data science, physics guided data science or knowledge guided machine learning model. Can they be made to produce results that are physically consistent? Can they follow the laws of the physical laws like conservation of mass, energy, and then so forth? Can they work with limited observation data? That is, what if you have very small amount of data? Can they leverage the physics, or can they leverage the knowledge or the science to reduce the reliance on large data? And then can they generalize to scenarios that are not given to them? That is, you looking at the going beyond the scientific, going beyond the statistical relationships that are present in the data itself. Can they provide novel insights without which, of course, you cannot advance the field? And again, the last question on this list may seem very incongruous, which might sort of seem, but how could you even talk about it? And this is about, can HTML models be used in an absence of observation data? What if I don't have anything observation? Can I still make use of them? And again, you will see talks in this workshop that are going to be covering many of these topics. I'm going to sort of give you sort of very simple taste of some of these questions answered in the context of a very simple system, a very important system, but relatively simple physical system, which is modeling the dynamics of temperature in lakes. We have lots of lakes in Midwest, and they are important for recreation and fishing and human consumption of water. And the dynamics of water temperature, temperature of changes, the quality, it has impact on the quality of the water and the quality of fish that can survive in it. And GLM is a state-of-the-art physics-based model that's used by USGS to model these lake systems. And the question is, and I'm going to sort of show you an answer to some of these questions, is to what extent the KGML paradigm could be used to help in this context. And I'm just going to go through it a little bit quickly, given the short amount of time I have. If you have a lake system like this, you have weather drivers, meteorological drivers like temperature, pressure, precipitation, and such that are readily available from climate system, which is the part of the big data. And then for some of these lakes, for example, lakes such as Lake Mendota, they have a lot of observations that are available to the USGS. And the idea would be that I have the drivers from the weather system, and I have the observations that are available. Could I build some sort of a machine learning framework? Could be a neural network, could be a recurrent neural network, to make predictions based upon these drivers and see the difference between those predictions and the observations to create a training loss and build this model. And this is the traditional paradigm of data science modeling, black box machine learning modeling, that you give me the data, give me the labels, and I will build a training loss, and I will regularize my optimization process through the complexity term to hopefully to generalize to other samples that are not in the training set. The two issues with this paradigm, one of them is the labels are scarce. Lake Mendota is very well observed for the last 30 years. You have thousands and thousands of observations, days of observations, but most of the lakes in the world or in the US have very few observations or no observations at all. So you can't train the models that are of high complexity. And as a result, the standard method for assessing generalization performance can break down. And the second thing is that what you're predicting could be physically consistent in many ways. For example, the lake water temperature relates to density, and the high density water should be sitting at the bottom. And if I'm predicting temperature that is not consistent with the density, depth density relationship, then I'm doing something wrong. Or if I am predicting temperature which does not conform to the law of energy conservation, then I'm doing something not quite right. So the question is, how do you incorporate that? And again, over the last 5-6 years, certainly in the last couple of years, a number of work have come up in which people would sort of add some sort of a physics-based regularization term to the objective function to make these systems learn to make them physically consistent. Okay. Now, one very important side benefit of being able to have the physics-based laws is that now you could learn even in absence of the observations. That is, if on certain days I don't have observations, I can still compute the physics-based laws. Of course, I do need observations to build the entire model, but if I have physics-based laws, I can even make use of the data on days on which I don't have the observations. And as a result, I can build a model like this. And you see this picture, the black portions are the black box data behind models, and the blue portions are the ones in which you're computing the energy flux terms, and you're creating a loss function. You're contributing a term to add to the loss function. And then in addition to this, you could also overcome the data sparsity challenge by pre-training with the physics-based model, because physics-based model can create unlimited amount of output, not the observation, but the output that are driven by the drivers. And if you can train your physics model, your machine learning model using them, maybe your structure would come close enough to the reality, and then you need only a small number of observations to get to where you want to get to. So there are many, many different ways you can bring in physics into, or the knowledge into, the machine learning framework. Now, just to give you a sense of how this paradigm works in this very simple model system, very important, but relatively simple model system, you can see here, the green you see here is a graphic. On the vertical dimension is the test RMSE. Lower RMSE is better, so the higher points in this curve are better. And on the y dimension is the number of profiles, number of days of data that were used to train it. And you can see if I have a genetically calibrated GLM, that means it has been used with, it has not seen any observation data. It has a high RMSE of 3, but as you use more and more observations to calibrate it, its performance improves. But if I build a black box, simple state-of-the-art black box LSTM, it actually, given sufficient amount of data, it can actually outperform even the GLM. At the lower end, of course, it does very poorly. But the beauty here is that this LSTM doesn't know anything about the physics or the situation here. But of course, this thing makes a good story for Lake Mendota, for which we have a lot of data, but most of the lakes don't have much data at all. So, but if you put the process, the knowledge, and the machine learning together, which is the purple curve here, and then you can see that it sort of exceeds both of them. And even at very, very small number of observations, it can do dramatically better. So this sort of shows the power of using physics to get handle the sparsity. Okay. Now, I just want to highlight this point just for a minute, just to show you that such models can actually also do wonderfully well in out of sample scenarios. So what you're seeing here are two graphs here. On the left side, only both of these graphics have been trained with 500 observations, 500 data points, lots of data. But on the left picture, they are the training and test are similar in the sense that they are given data from the same seasons, spring, fall, and winter, and summer, and the testing also have the similar range of data, but they're from different years. Now, on the right side, the training and tests are from different years, but the test from the training and test both, we hide from the training, we hide the data for the summer. And as a result, what you see is even the process-guided machine learning, process-guided models, green model, drops in performance. The machine learning model, the orange one, drops dramatically. Okay, and but the process-guided machine learning model drops, but very little. So what you're seeing here is a situation in which so the fact that the RNN, the orange model, dropped so much is not a surprise, because black box model cannot work with situations that they have never seen. So basically, the training has never seen any data from summer. It's supposed to do very poorly. The green data is the physics model, but the green data has been calibrated using data only from spring, fall, and winter. It has never been shown the data from summer. So it drops dramatically because it doesn't have the proper calibration. But the data science model, by having learned both from the physics and the observations, which are actually from spring, fall, and winter, not from summer, it actually does dramatically better. So what happened in this case is that it learned the PGRNN learned the structure, overall structure from the GLM, the green model, and it learned the biases which sort of carried over on all seasons from the spring, fall, and winter, and it just did beautifully in the summer, relatively speaking. Okay? And this slide just simply shows that, yes, you can also use these PGRNN type models to also ensure energy consistency. So just since my time is up, I'm just going to conclude with my final remarks here to say that this paradigm of knowledge-guided machine learning offers, it's a promising direction for addressing limitations of pure machine learning models or pure process-guided approaches. And then you saw some preliminary results in the context of modeling temperature dynamics of a lake, but you're going to see in this workshop, in the remaining sessions spread across 3 days, this paradigm illustrated by number of speakers in many diverse domains. In fact, just the speaker who's coming right after next is going to be talking about quantum mechanics and fluid dynamics, in addition to aquatic systems, and how some of these methods can be used. And of course, what we're talking about here are just some very early and preliminary results. There's a long road for us to traverse collectively as a community. And one of the big questions, and it's a single bullet here, but it's a really big question, is how do you incorporate the complex physical knowledge, which can come in many shapes and forms, into the model learning and model architecture form, in the sense that, is it, and I suspect that as we work in this direction, as we work with different applications, we are going to see, not too far into the future, machine learning frameworks and paradigms that will revolutionize perhaps data science for everybody, just like the adoption of CNNs driven by the needs of the vision community, and RNNs and LSTMs driven by the needs of the speech and the language community have really revolutionized how we solve many, many problems. Then there are systems in physical sciences that have multiple components. I showed you a system of a single lake, but you can have network of streams that are interconnected. You can have a complex hydrological system, which may have, the surface hydrology, could have groundwater hydrology, could have evaporation from the crops on the ground, the trees and vegetation on the ground. Completely different physical systems. Each of them play their own role. And again, look at the global climate system. We're talking about far, far more complex situations there. And when you have these different components, how do you model each one of them using this KGML paradigm? How do you model them collectively while keeping the relationship among them scientifically correct, and then so forth. And so these are all the slide, the bullets 1 and 2 are actually very, very complex in many ways. And the last one, I'm just sort of talking about a bullet here as a direction which is sort of completely novel, or I should say completely foreign to the machine learning community, in the sense that we are used to building a model in which we're given the data and we make the prediction. And in many of the scientific scenarios, actually, there's a notion of data assimilation, which is as you make predictions and you observe the state of the system or some aspect of the system, and then you use that to make corrections in your state of the system that you're making use to make future predictions. And how do you bring this notion of data assimilation in this machine learning or the knowledge-guided machine learning setting? So these are some of the questions that I believe that need to be addressed. And of course, as I said, we have a rich program. We have a great set of speakers, and they will be bringing their perspective. And like you, I am looking forward to listening from them and learning from them. So with that, I guess my time is up, and I'm going to...
Yes, Vipin, there are no questions for this first session.
Okay, so maybe we should